Disclaimer, disclaimer, disclaimer! What you are about to hear is the mild rantings of a high school physics teacher who stayed up way too late trying to figure out what G-2 means, and then got up early in the morning, drank way too much coffee, and then tried to explain this to you. Thank you. All right, I'll try to do my best to explain what's going on here. Let's start off with something that we know. So let's say we, you know that opposites attract and likes repel. Okay, so if I have a negatively charged particle and a negatively charged particle, they will repel from each other. Okay, whoa, I did that the wrong way. There we go. They repel each other. That's some simple middle school, maybe high school physics going on here, because we can calculate the force, blah, 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 blah. But how do they do it? Like, they don't even touch each other. How do they do it? Well, there's some field that's going on. And when there's a field that's going on, particle physics and quantum physics says that there has to be an exchange particle that carries that force. Okay? So if I do that, I'm going to put in this field-carrying, force-carrying particle that causes it to break apart. Yes. Okay, that is a thing. So we took a known idea of two particles that are similarly charged. Why do they repel? Because they have this exchange particle. Okay, so let's build upon that. The particles in this new study, the muon, are literally, so the muon is shaped as the Greek letter mu, and it is negatively charged, and it has a mass of about 212 times that of a electron. Okay, so it has the same charge, but it is heavier. All right, and if we stick that in, as we'll call it a circle there, particles tend to have a little spin to them, like a top, and we'll see that spin kind of wobble and progress, and then it comes back. Whoops, I should have changed. Then it comes back to its original position, and okay, so we can time that. All right, and if we do time it, we can come up with a frequency. So that's how we detect these small little intrinsic values. So we can detect the negativeness of the particle itself, and we can detect its wobbly nature of it. Okay, so why does it wobble? That's the question. Okay, so that's what we're really that's what the folks are really looking at. Not we. I didn't do anything. All right. So now we're going to go down a different path here. So let's say I have a muon traveling along in this path, and then for whatever reason, it goes off to the side because it gave off one of those particles. And kind of like you walking down the hallway and me throwing a bowling ball at you, you would interact. Well, this is more like an explosion. Maybe there was some other muon sitting way out here, but it gave off a particle. Okay, so that can be easily explained. Here's where it gets creepy. Here's where it gets crazy. So the model that we have in physics right now explains that. It also explains maybe, oh, sorry, let me back up. And in this simple little diagram that I've got here, you do a whole bunch of math that I don't do, and you come up with this factor of spin. Remember those wobbles and whatnot. That was supposed to be, if we added up all the probabilities, there's this factor of 2. Yep, a bell just rang. So yeah, we get to 2 of a probability of the property of the spin. But sometimes it doesn't quite happen exactly like that. And here's something crazy. Maybe this muon gave off another particle and then reabsorbed it. That could change its intrinsic value. Maybe it did so over here. Maybe, just maybe, it did something like this. It produced this light carrying, it's called a photon, but maybe that photon broke up into these two other particles. Maybe one's a positron and another one is a virtual proton or something like that. And then it came back and then re-emitted it. And we wouldn't necessarily be able to see that, but we could see that it didn't quite add up to 2. So we have to add these zeros over here, and we'll get to, it's like if we added up all these possible parts that it could break up into. So maybe this is some kind of another lepton or a Higgs particle, but the Standard Model, so the Standard Model made this prediction using quarks and whatnot, all the particles that we know of, that the momentum, that this G factor that they're calculating should add up to 2, and then if we add up a whole bunch of the virtual particles, it goes to 2.002. Okay, so that didn't happen. When they're actually doing the detection, it came out to something more like, I'm making up the numbers here, but it said G was 2.002136114. Someplace way down here, the numbers wouldn't match up, or this number might have been 0006, and so the numbers didn't quite. That's why it's G minus 2. This is a G value. This is a G value. So G minus 2, and then we get all these decimal points. All right, that's not a big deal until physicists are like, none of our particles that we've discovered so far do this interaction down here. We don't have a reason for that to happen. Probability is really low. It's really hard to detect. But there's nothing in the Standard Model that says that a particle, even if it was some crazy thing that was going on here, we don't have any. So it's an unknown. So that unknown that's when things get exciting, because now we're looking for something new that nobody's seen before. First, they got to make sure that this wasn't just a screw up of their machine, which they're very close to doing that. They're going to run some more trials, but within this unknown holds a lot of possibilities. You ready for the deep dive? This is the rantings of a high school physics teacher. All of this is contained in something that the physics within the Standard Model predicts how the electromagnetic forces interact. That's what's going on here. Got a negatively charged particle, the two repel each other. That's electromagnetism, and we can predict. They've been doing a really good job of predicting all these interactions. It works. Okay, but then now we have an unknown. What is that? Deep dive. One of the big goals of particle physicists and physics in general is to come up with a theory that explains how electromagnetism works and how gravity works. Gravity is so weak that we haven't been able to find any particles. We've found a wave, but we haven't found any particles of interactions. And, oh boy, here we go. If there are these unknown particles in here, maybe that'll get us a step closer to how particle physics connects with gravity. And if we can unify these two ideas, electromagnetism and gravity, by the way, physicists call this a grand unification theory. It's like the big, yes, it's got a big, huge goal. And if we unify electromagnetism and gravity, we know that in the Standard Model we have protons, but we also have antiprotons, and when matter and antimatter come together, they annihilate. Follow me down the deep well here. If we can connect the Standard Model of electromagnetic particles to gravity, maybe at some point in time we can find anti-gravity. And if an anti-gravity is found, we can make the inertial dampeners that Star Wars predicted, and we can finally make the jump to light speed. That's why this is so important. Have a good day.